This is the first of two lectures on general changes of variable for multiple integrals. We've already seen changes of variable, in fact. Going from Cartesian to polar coordinates is a change of variable. Going from Cartesian to cylindrical or spherical coordinates is a change of variable. In these lectures, we're going to introduce the idea of a transformation, a new kind of derivative, the Jacobian of a transformation, and we'll use it to fully develop the change of variables technique for multiple integrals. So in this lecture, we'll understand what a transformation between two regions of the plane is. And we'll understand how to compute something called the Jacobian matrix and Jacobian determinant of a transformation, and understand what the Jacobian determinant, this new kind of derivative, measures. We'll use this machinery to understand how to compute double integrals using the change of variables formula that we'll introduce. So first of all, I want to remind you how change of variables works in Calculus 1. You might know it more familiarly as U substitution. So if we have a map, x equals g of u, from one interval to another along the real line, then I can recognize an integral like this, right, as really just being this integral. In other words, there is the change of variables formula for one variable calculus looks like, if you make the substitution x as a function of u, then the integral from a to b of f of x dx is the same thing as the integral from c to d. Let's see, where did the interval from c to d come from? The map G takes CD to AB. So the original integral is the integral in the change of variables, and there's a factor here. This factor, you might say, measures how the transformation changes lengths on the real line. What we're going to do is we're going to develop in two variables an analog of this factor, which is going to be something called Jacobian. So here's a preview. We're going to take this apart and discuss it in detail in the lecture to come. But here's a preview. For a plane region, a change of variable involves two functions. And it involves regions in a UV plane, so that's a two-dimensional space, a region in the UV plane. If a region S from the UV plane is mapped to a region R in the XY plane, then the integral over R of a function f is the same thing as the integral over S of f with this change of variables, where there's a factor called the Jacobian, which we're going to introduce. You don't know how to calculate it yet, but we will. And what it measures is how areas change in this map from U and V to X and Y. So there's a very precise analogy between this one variable version of change of variables, U substitution, and what we're about to do today. The first thing I want to do is introduce the notion of a transformation. And I'm going to do that by using something that's already familiar to you. Namely, you know about the polar coordinate map. So the polar coordinate map, I'm using that word, sort of a new way of looking at what we did, defines a transformation from a region S in the R and theta plane to a region in the XY plane, a region R, which we called a polar rectangle. So let's look at the corresponding sides of the rectangle in the R theta plane, that's the rectangle S, and the polar rectangle in the XY plane. So first of all, if I move from angle beta to angle alpha in the R and theta plane, that's like moving along this side of the polar rectangle. I'm changing theta from beta to alpha. So this corresponds to the line R equals A. That's this line here. R is constant and theta is changing. That gets mapped to this side of the polar rectangle. Next, as I'm traversing the rectangle in the R theta plane, the next side is where the polar angle changes, but the radius goes from A to B, and that's traversing out along here, changing the radial coordinate r, but keeping theta fixed. So that's the line theta equals alpha in the r and theta plane, getting mapped to this side of the polar rectangle. Thirdly, as we traverse this side of the rectangle in the r and theta plane, what happens in the x and y plane? Well, let's see. So r is fixed at b, but theta is going from alpha to beta. So that means we're traversing this side of the polar rectangle. Finally, to complete the round trip, we fix the angle beta and go from r equals b back to r equals a. Which side of the polar rectangle is that? That's this side here. So these two equations define a transformation from the r theta plane to the xy plane that map a honest-to-God rectangle into a polar rectangle. So in order to prepare the way for discussing more general transformations from the UV plane to the XY plane, I just want to change some names. I'm going to change the name of R, the radial coordinate in the polar coordinate map, to U. And I'm going to change the name of the angle, the theta coordinate, to V. Otherwise, these formulas are just the same formulas with new names for the variables. They define a transformation from the UV plane to the XY plane, which maps the honest-to-God rectangle to the polar rectangle. Let me remind you how that works. So as we traverse the line U equals A from V equals beta to V equals alpha, that means I'm moving in this direction in the polar rectangle. As I next traverse the line V equals alpha, where U ranges from A to B, I'm moving from the inner radius to the outer radius of the polar rectangle. As I traverse the line U equals B, where V is varying from alpha to beta, I'm moving along the outer radius of the polar rectangle from angle alpha to angle beta. And finally, as I traverse the line V equals beta, from R equals B to R equals A, I'm going back from the outer circle to the inner circle. So that's how this transformation of a rectangle into a polar rectangle works. But now what I'd like to do next is analyze other kinds of transformations. But now I want to look at something different. I want to look at a transformation other than polar coordinates. Remember, what a transformation is supposed to be is a change of variables from U and V to X and Y given by a formula that computes X in terms of U and V and Y in terms of U and V. So here's a different set of formulas, and I want to explore how those formulas work. What happens to the unit square in the UV plane? And my claim is that it gets mapped to this rather different region in the XY plane, which is really kind of amazing. So let's try to step through that. So first of all, what happens when U goes from 0 to 1 and V is fixed? V is fixed at 0, in fact, so that means that the Y coordinate, if V is 0, is going to be 0, so I'm going to be moving along the XY plane. I'm moving from where to where. If V equals 0, then for the X coordinate, I get that X is U squared. So as I traverse from U equals 0 to U equals 1, indeed, I just move from here to here. Okay, so that's pretty easy. What happens next as I fix U at 1 and I move up along the square from V equals 0 to V equals 1? Then you can work out what the formulas are. If U is 1 and V goes from 0 to 1, then this side is mapped into a parametric curve, right? V is a parameter. What that parametric curve is, you can work it out. You can eliminate the parameter, right? We did this, or you've done this when you've studied parametric curves. If X equals 1 minus V squared and Y equals 2V, then V, the parameter, is Y over 2. So that means x is 1 minus y over 2 squared, or 1 minus y squared over 4. So now I know exactly what this curve is because I eliminated the parameter. There it is. It's a piece of sideways pointing parabola. And it goes when x equals 1, y is 0, and when x equals 0, y is 2. You can see that from this formula. So that's the second part. So we went from here along here, and that corresponds to traversing from here to here. What happens next? If we now set v equal to 1 and move from 1 to 0 in u, again, I can go back to the formulas, set v equal to 1, and I get x equals u squared minus 1 and y equals 2u from the formulas up here. Once again, I can eliminate the parameter to see exactly what this curve looks like in the xy plane. So let's just do that. The easiest way to eliminate the parameter is to use the second equation and write u, the parameter, is y over 2. And so I see that this new curve is x equals y over 2 squared minus 1, or y squared over 4 minus 1. That's the graph of another parabola that opens out this way, but it's now restricted to, let's see, if u runs from 1 to 0, then y runs from 2 to 0, and sure enough, the curve that we traverse is this curve along here, going down back to the x-axis. The final step in our traverse is going to be the following. So I'm now going to move when u is 0, I'm going to move along v from 1 to 0. So once again, I can go back to the equation, set u equal to 0, and I see that I get the following thing. So if I just look at if I substitute u equals 0 into the equations, I get x equals minus v squared and y equals 0. Phi is going from 0 to 1, so that means x goes from minus 1 to 0, and sure enough, I'm moving along this curve. This should say here, let me correct a small typo here, this should say minus, whoops, sorry. This point is minus 1, 0. So this new transformation, it's not polar coordinates, but it's some other thing. This new transformation defined by these formulas takes a unit square and maps it onto this shape, this unusual shape that looks sort of like a Gothic arch. So what you have to imagine is a situation where you want to integrate over a region that looks like this, which looks like a real pain to integrate over, right? You've got to set up two separate integrals using these conditions. But when you have this nice map, if you can make a transformation, a change of variables work, you can calculate the integral over this region by changing variables and integrating over a unit square. That seems like a pretty cool idea. So let's take a look at another transformation and see if we can understand its action in the xy plane. So you're going to start out again with a rectangle in the UV plane. And we have a formula for the transformation, x in terms of u and v, and y in terms of u and v. We want to work out what region this is mapped to. So the right way to do this is to make a table. We know that points in the UV plane are going to be mapped to some corresponding points in the xy plane. Let me remark that this transformation is an example of what's called a linear transformation. X is a linear combination of the variables u and v, so it's a coefficient times u plus another coefficient times v. Transformations of this type always map quadrilaterals into quadrilaterals. So the best way to understand the action of this transformation is to make a table where I list the vertices of this rectangle in the UV plane, 0, 0, 3, 0, etc. And then I use these formulas to calculate the corresponding points in the xy plane. That's what I've done here in this table. You can check to see that this is correct. So if I look at the images of the points, let's see, so 0, 0, I'm told maps to 0, 0, so there's 1 point. Let's just step through the table. The point 3, 0 maps to the point whose coordinates are 6 and 3. So as I go from 0, 0 to 3, 0 in the region S, I'm going from here to here in the XY plane. Let's see what point we visit next. So the point 3, 2 out here gets mapped to the point whose coordinates are x equals 12, y equals 1. So as I move from here to here in the UV plane, that's moving from here to here in the XY plane. Finally, the point, so if I move from here to here, I'm moving from 3, 2 to 0, 2. That's moving from 12, 1 to the point 6 minus 2. So I move from here to here to here. And of course, I move back to the starting point. So here's what I've now learned. I've learned that this transformation, which I said is a kind of linear transformation, it just involves a number times u and another number times v for both x and y. This linear transformation takes a rectangle in the UV plane and maps it to a parallelogram in the XY plane. Now again, you can see that this could be a very useful tool if you could somehow figure out how to take a change of variables and do a double integral that way. This nice rectangular region is much simpler to integrate over than this parallelogram. The trick, of course, is to find the right change of variables. That's something we'll return to. So here's our complete picture of the transformation. The transformation defined by these equations takes the rectangle and maps it to this parallelogram. Okay, so we now come to checkpoint 1. I've given you a transformation. X is equal to a times u and y is equal to b times v, where a and b are numbers. And I've given an initial region in the UV plane, which is just the disk, u squared plus v squared is less than 1. So it's a unit circle. And my question is, what sort of figure is it mapped to under this transformation? Now I'll tell you a useful thing to do may be to solve this transformation for u and v. So u is going to be x over a, and v is going to be y over b. Let me write that a bit more neatly so it looks more legible. V is going to be y over b. So what region corresponds to u squared plus v squared less than or equal to 1? Well, you can re-express that region in terms of its image region in the x's and y's just by substituting these into the equation. So then my question is, what's the resulting figure? So take a couple of minutes and see if you can puzzle this out. Let's take a look at this example of a transformation in checkpoint 1. If, as I suggested, I solve for u and v and substitute them in the equation in order to find out what the image region in x and y is, what I get is x over a squared plus y over b squared is less than or equal to 1. You can recognize this if the inequality were replaced by an equal sign as the equation of an ellipse with semi-major axis A and semi-minor axis B. So what the image region is the following. It's actually an ellipse that cuts the x-axis at x equals a and the y-axis at y equals b, and of course also at the negatives of those 2 points. So this transformation maps a circle into an ellipse. Now once again, you can imagine if we could just get this change of variables thing off the ground, suppose I had to integrate some function over an ellipse. I could use this transformation to reduce that integral to an integral over the unit disk and maybe use polar coordinates, for example. That's why these things are going to be useful, and seeing that in action is coming. Now, as promised, I'd like to introduce this new derivative, the Jacobian, for a transformation that measures how areas change under the transformation. So let me remind you that in one variable calculus, if I make a transformation x equals g of u, I can calculate using the derivative of the transformation g how lengths change. If on the real u line, I go from u to u plus delta u, and I look at the corresponding image points, u goes to g of u, and u plus delta u goes to g of u plus delta u, then the distance from here to here under the map becomes the distance between these 2 points. And by linear approximation, the distance from here to here is approximately the size of the derivative times delta u. That's just linear approximation. What we're looking for now is a similar derivative for 2 variable transformations, where x is a function of u and v, and y is another function of u and v. So what will turn out is that the change of areas is measured by this derivative, which is really the determinant of a 2x2 matrix of derivatives of the maps. So that delta A in the xy plane is going to be the Jacobian times the area of the little rectangle in the UV plane. And I'd like to see why that's the case. In order to do that, I want to introduce a slightly different way of looking at transformations. So far, we view transformations as 2 equations, one for the x and one for the y. But I want to introduce another way of looking at it as a vector function of 2 variables. So the input is the 2 variables u and v, but the output is a vector whose components are the x of u and v, which is just another name for g of u and v, and y of u and v, which is another name for the function h of u and v. For example, if I wanted to write the polar coordinate map in this new way, the vector function would have components u cosine v for the x and u sine v for the y. This vector function has partial derivatives, which are themselves vectors. I want to talk about them for a minute and illustrate what they mean. So by r sub u of u and v, I mean the vector function of u and v, where the first component is the derivative dx du, and the second component is the derivative of y, dy du. R sub v means the derivative of this vector function with respect to v, where again I take derivatives on each component. What do these derivatives mean? This is going to be very important to understand. So let me illustrate the meaning of these derivatives with a transformation we've looked at before, the transformation from the unit square into this church window shape. So what does the partial derivative of r with respect to u actually do? Suppose that I fix v at 1 and I move along u. Let me remind you that this curve maps to this curve here. So the straight line maps to this curve in the image. And this point maps to the blue point here. So what the derivative here is really just doing is giving the tangent vector along this curve, shown in red. So that's what the derivative of r with respect to u for fixed v does. Fixing v means that we're traversing a parametric curve with u as parameter. And when I differentiate with respect to u, I just get the tangent vector. Similarly, I can think of this derivative r sub v as follows. I now look at v changing for fixed u. In this case, u is 1, and as v varies, I trace out this curve. So the derivative r sub v evaluated at u equals 1, v equals a half is just going to give the tangent vector along this curve. So these derivatives tell me how the function r of u and v changes if you change one of the coordinates. That's going to help us understand how areas change under a transformation. Let me think of a transformation from uv to x and y in this way as a vector valued function. And what I now like to do is I'd like to calculate, if I begin with a very small rectangle of sides delta u and delta v, I know I'm going to get some kind of parallelogram generally in the xy plane. And I want to know the area of this guy in terms of the area of this guy. In fact, I want to know what the multiplication factor is. That's exactly what we're going to do. So I'm going to use these two derivatives to do the following thing. The derivative of r with respect to u is going to tell me if I make a little displacement in delta u, how far do I go in the xy plane? Well, I go along that vector, r sub u times delta u. If I make a displacement delta v, what's going to happen in the xy plane? I make a displacement given by that derivative dr dv times delta v. So remember that the area of a parallelogram is the cross product of these sides. So if I now take the cross product, let's do a little side calculation here. So the area of r is going to be the magnitude of the cross product ru delta u cross rv delta v. The delta u and the delta v are just scalars. So what I get is ru cross rv magnitude times delta u delta v. So the area of the parallelogram is exactly the area of the rectangle times a factor. So this ru cross rv is exactly the multiplication factor for area that describes how area changes as I move from the uv plane to the xy plane. If I remember now the definition of ru and rv, I can calculate this cross product. So let's do that. So we concluded that the parallelogram, the image parallelogram in the xy plane, that's what S maps to, has approximate area ru cross rv times delta u times delta v. To calculate this cross product, I just put the vectors ru and rv into the usual 3x3 matrix for the cross product. You can work out that the only non-zero component of this cross product is going to be the k component, and that the magnitude of that k component is exactly this. It's dx du times dy dv minus dy du times dx dv. So that's the area stretching factor that I'm looking for. So what I get is that the area of r, which is like my dA in a would-be integral, is just the area of S times this factor, where this factor is what's called the Jacobian determinant of the transformation. Okay, so let's just try to calculate some of these Jacobian determinants. Let's do an example. Let's take the example of that linear transformation we looked at that mapped a square to a parallelogram. So in order to compute the Jacobian determinant, the way I set this up is first compute all the derivatives. So dx du is 2, dx dv is 3, dy du is 1, dy dv is -1. So I'm getting these partial derivatives from these formulas up here. So what's the Jacobian determinant? It's the determinant of a 2x2 matrix formed from these derivatives. What is that? That's -2, -3, or -5. That's the Jacobian determinant of this transformation, which I said was an example of what's called a linear transformation. Okay, again, just to get a little bit more practice, let's find the Jacobian determinant of the transformation that mapped a circle to an ellipse. I form the derivatives. Dx du is the number a, whatever it may be. Dx dv is 0. dy du is 0. dy dv is b. Again, where am I getting these partial derivatives from? By taking partials in these formulas. So now I formed the determinant. It's going to be a, 0, 0, b. So the result is that the Jacobian determinant of this transformation is just a times b, the number a times the number b. Okay, so now we come to checkpoint 2. I'm asking you to find the Jacobian determinant of that transformation which mapped a square into the sort of church window shape. So take a minute, compute the Jacobian determinant. It will be a function of x and y, excuse me, a function of u and v. Let's see if you can compute that determinant. Let's compute the Jacobian determinant by first writing down the derivatives. I'm going to take derivatives in these expressions. So I get dx du is 2u, dx dv is minus 2v, dy du is 2v, and dy dv is 2u. So the Jacobian determinant is what I get when I put these derivatives into a 2x2 matrix and evaluate the determinant. That's going to be 4u squared, and taking account of the minus sign, plus 4v squared, or 4 times u squared plus v squared. So in this case, the Jacobian determinant depends on u and v. I'd like now to look at how this Jacobian determinant stuff works out for transformations we already know. So let me just walk you through this calculation. Again, the way I form the Jacobian determinant is I look to these expressions to take derivatives. Dx du, if x is this, it's just the cosine of v. Dx dv is minus u sine v. Turning to the derivatives of y, dy du is sine v. Dy dv is u cosine v. So when I put these 4 derivatives into a 2x2 matrix and take the determinant, let me just show you an intermediate step in the calculation. So I get u cosine squared v. Then taking account of the minus signs, plus u sine squared v. And that's why I get u for the Jacobian determinant. That seems strangely familiar, right? So let's back up here. That seems strangely familiar, right? If I renamed u and v r and theta, what this Jacobian factor would be is exactly this mysterious r that shows up in the formula for polar integrals. So what this is, what the mysterious r is exactly the area change when you go from a small box in the uv plane or the r theta plane to a polar rectangle in the xy plane. Okay, so just to make clear some notation that we're going to use in what follows, when I write this shorthand, what I mean is the determinant of this 2x2 matrix, which could be positive or negative. But when I put absolute value bars around it, that means I'm going to take the absolute value of the determinant, and that's always a positive number. That'll be very important to know about as we move forward, because now it's time to talk about the change of variables formula. So here's the deal. If I have a transformation that maps a region S in the UV plane to a region R in the XY plane, suppose my goal is to integrate a function f over that region R. So we know that any double integral is approximately a double Riemann sum. Now, but I could view each of these points, xi and yj, as image points under the transformation of a ui and a vj. So f evaluated at those points is going to be the same, but now what about the area? Well, I know that the area change from the rectangles in the UV plane to rectangles in the XY plane, that is from this to that, is exactly the absolute value of the Jacobian determinant. So what that suggests is that I should be able to rewrite this integral as the limit of this second Riemann sum, which is going to be the integral over S of f in the new variables, integrated over u and v, but multiplied by the area change factor. So here is the change of variables formula in a double integral. If t is a one-to-one transformation from a region S that lives in the UV plane to a region R that lives in the XY plane, then the double integral over R of a function f is the double integral over that region S of f in the transformed variables times the area change factor, du dv. So this is the promised change of variables formula, which, if we're clever enough to find a good transformation t, allows us to convert integrals over complicated regions like a parallelogram or a church window shape into an integral over something simple like a rectangle. So now we're going to see exactly how that works. So now let's see if we can actually compute an honest-to-God double integral using the change of variables formula. So the task is to compute this integral, where R is this triangular region that looks like that. That's going to be a really, really tough region to integrate over in x and y coordinates because you'll actually have two different regions, one where the y goes from here to here, and one where the y goes from here to something else, so that doesn't look like a lot of fun. But fortunately, the claim is that there's a very nice transformation that will turn this triangle into something simpler. But we've got to understand what that simpler region is by taking the x and y vertices and figuring out what u and v they came from. So step one is going to be to solve for u and v in terms of x and y. So I've done this. Let me go quickly through the arithmetic. If x is 2u plus v and y is u plus 2v, suppose I now want to solve for u and v in terms of x and y. Let's see. So this is linear equation stuff. I get 2y equals 2u plus 4v. If I subtract, I get x minus 2y equals minus 3v. I can solve that equation to get v is equal to 1/3 times 2y minus x. You can do a similar manipulation to get the other formula that u is 1/3 times 2x minus y. Okay, so the first step is to solve for u and v in terms of x and y. Take the given formulas for the change of variables and invert them. What's the second step? The second step is to determine the region S in the UV plane that corresponds to this triangle. And fortunately, this works out very nicely. So I'm going to take my equations for u and v, and I'm going to make a table where I take each of the three ordered pairs in the xy plane, here, here, and here, and use these formulas to figure out what their corresponding points are in the UV plane. So the point 0, 0 corresponds to the origin. The point 2, 1, that's up here, corresponds to the point 1, 0. And finally, the point 1, 2 up here corresponds to the point 0, 1. So it's fabulous. This transformation, x equals 2u plus v and y equals u plus 2v, maps this very nice triangle into the region I want to integrate over. So I'm good to go for the change of variables. So now that I understand what region in the UV plane corresponds to the region I want to integrate over in the XY plane, what's the next step? So I need to find the Jacobian of the coordinate transformation, because remember, that's something that I need for the change of variables formula. So now let's find the Jacobian of the coordinate transformation. What's the Jacobian matrix? Remember, it's dx, du, dx, dv, dy, du, dy, dv. I read those derivatives from these formulas, and you can work out that dx du is 2, dx dv is 1, dy du is 1, and dy dv is 2. What's that determinant? It's exactly 3. So the Jacobian determinant is 3. So now we come to the final step where we're ready to compute the double integral. Let's first express x minus 3 in terms of u and v. This is making the change of variables. That's this step in the substitution. So x minus 3y is equal to 2u plus v minus 3 times u plus 2v. Collecting terms, 2u minus 3u is negative 3u. V minus 6v is negative 5v. So the double integral of the function x minus 3y over the original triangular region R is the same as the double integral over the region S of minus u minus 5v, then times the Jacobian of xy with respect to u, then du dv. So I now want to write the integral over S as a double integral. There are at least 2 correct ways to do that, but let's just write it as the integral from 0 to 1 over u. Then for each u, v goes from 0 to 1 minus u. The integrand is minus u minus 5v. Then to Jacobian is 3, dv du. Okay, so just identifying all the pieces here. The du dv is here. The Jacobian is here. And the integrand with the change of variables is here. I'm not going to actually calculate this out. This is now a very simple double integral. By now, you all are aces at doing. So that's using the change of variables formula to reduce the integral over a complex region to the integral over a simple region. And again, the trick is to find the right transformation that maps the simple region over here in the UV plane to the desired region in the XY plane. So we now come to checkpoint 3. What I'd like you to do is I'd like to use this transformation, which you've studied before, and we know maps a disk of radius 1 into an ellipse in the XY plane. I'd like you to use that transformation and its Jacobian to compute the area of the ellipse by reducing it to a double integral, the disk, of radius 1 in the UV plane. Let's take a look at the double integral in checkpoint 3. So we know the transformation is x equals a times u, y equals a times b. You can look back to a previous part of the lecture to see that we calculated the Jacobian of this transformation as just AB. So the area of the ellipse is the double integral over this region R of the function 1. Okay, just to make sure it's clear what R and S is, this is R, that's S. So I know what the change of variables tells me is that's the same thing as the double integral of S, the same function. It's like really easy to do the substitution as the constant function 1. Then I've got the Jacobian, then times du dv. Okay, so what are the corresponding bits here? The Jacobian is here. The du dv is here. And finally, the function is here. Okay, so now here's what I want you to notice. The double integral in S is just over the unit circle. So I really don't have to compute anything because I know exactly what the area of the unit circle is. The area of the unit circle is pi r squared, right? So I just get pi times a times b, and that's the area of the ellipse. Done. We introduce the notion of a transformation from the UV plane to the XY plane. Transformations are something we've actually already seen. The polar coordinate change of variables is a transformation from r and theta to x and y. We introduced what's called the Jacobian determinant of a transformation, which measures how areas change under that transformation. And we learned how to compute the Jacobian for some simple transformations. The main event was the change of variables formula, which allows us to compute a multiple integral over a complicated region if we can find a transformation that maps a simple region to that complicated region. And we worked several examples of the change of variables theorem. In the next lecture, we'll see some more examples of how the change of variables formula works, and we'll also extend it to triple integrals in 3 dimensions.